All right, so let me say what Riemann thought of as, how Riemann thought of the curvature tensor as the obstruction to the manifold being Euclidean, the Riemannian manifold being isometric locally to Euclidean space. So it turns out that if so R is the curvature tensor of M, a Riemannian manifold. So then what Riemann showed in his initial talk on Riemannian manifolds, where he introduced the concept of Riemannian manifolds, was that R is identically zero. The curvature tensor vanishes identically if and only if M is locally isometric to Euclidean space. So that means every point has a neighborhood which is isometric to an open set in Rn. Okay, so one direction should be clear, right? If M is locally isometric to Rn, then the curvature tensor of Rn is zero, right? And so the curvature tensor of M will be zero. And conversely, if the curvature tensor vanishes, then you can show that M is locally isometric to Rn. So I'll just give a quick sketch of the proof. Any questions?
No.
Okay. So first you show that R equal to zero. This implies that for all paths gamma in M, parallel transport along gamma is invariant under fixed endpoint homotopy of gamma. Or in other words, it only depends on the fixed endpoint homotopy class of gamma. Okay. Okay, so what this means is if you have two curves which are fixed endpoint homotopic in M, okay, so that means you can find a continuous one parameter family of curves with the same endpoints which interpolate between the two curves. Okay. Then parallel transport along the bottom curve is the same as parallel transport along the top curve if the curvature tensor vanishes. Okay, so how do you prove this? So you take the homotopy H between the fixed endpoint homotopy between the two curves. Okay. So it's a map from the unit square into the manifold. And what you do is you divide up this unit square into small squares of size 1 by n, okay, where n is some large integer. Okay, so this point will be 1 over n, capital N, and this will be 1 over capital N. And now you use the fact that parallel transport is along a small loop is identity plus t squared times the curvature operator, right? Okay, so if I look at, let's say, this first square here, okay, let me zoom in on this first square here. So if I expand this, so I have this square with sides 1 over n. Okay. And so let me look at this point. So then what I know is that if I look at parallel transport along this square, that is the image of this square. Right. So if I call this, say, P is parallel transport along this loop. That means the image of the loop here. So that will be something like this. Okay. And then P is going to be, so P goes from, so if I call these vertices, so the image, these correspond to vertices in M. So let me just label these vertices. So what should I, so well, this is the starting point, right? So this point maps to the starting point. So let me call this P and this is Q. So this parallel transport along this loop goes from TPM to TPM. Okay. And what I know is that P minus identity divided by 1 over n whole squared, this is equal to the curvature tensor, right? R applied to the appropriate vectors here, plus little o of 1, right? As n tends to infinity. Yes?
Yes.
So R is 0. So what do I get? So I get that P is equal to identity plus little o of 1 by n whole squared, right? Okay. Yeah, is this clear?
Yes.
Since R is okay. Now let me look at parallel transport along this top side. Okay. So let me call that Q. R is transport along this top. Okay. So therefore, if I look at Q composed with P, okay, so this point maps to some other point here, to some point here. I don't know, let me just call that for the time being, say R. Okay, so this point maps to some point R. So Q composed P goes from where to where? It goes from TPM to TRM, right? Okay. So since P is identity plus little o of 1 over n whole squared, and so that means that Q composed P will be equal to q plus little o of 1 over n squared, right? Yes?
Yes.
Okay. So now what does this mean? What is parallel transport? This q composed p. That means you go along this loop and then go along q, but going along this side will cancel going along this side backwards, right? These two will cancel. So this q composed p, this is parallel transport along this curve. Okay, right? Yes?
Yes.
And q, this is q is parallel transport along the top side. Okay. Is this clear? Yeah.
Yes.
So that means parallel transport along the top is almost the same as parallel transport along this curve with an error which is little o of 1 over n whole squared. Okay, now you repeat this for all the squares going from 0 up to 1, right? So if you repeat this for all the squares, you get a picture like this. Okay, so what will the picture be? So either you go along the top, right? Okay. And then you keep going along these small horizontal segments along the top. Or instead of going along the top, I can go along these U-shaped paths like this, right? Like this, and then like this. And then like this. And then like this. And then like this. And then like this, right? Make sense?
Yes.
Okay. So, okay, so either I'm going like this along these horizontal segments, or I'm going along the U-shaped segments, right? Now, the error, the difference between these two is little o of 1 over n squared. So when I repeat this capital N times, right, I'll get that the total parallel transport from here, from the top, this top left to the top right point. Yeah, if I call this composition, let's say, what should I call it? This is going to be, say, Qn up to Q1, right? And this composition below will be P P1 up to Pn, Pn up to P1. Okay, so then because at each stage I have an error which is little o of 1 over n squared, when I compose, I'll get this is equal to capital N times little o of 1 over n whole squared, right? Okay. Yeah, so this is Q1, Q2, Qn. This is P1, P2, Pn. All right. Yes.
Yes.
Okay. So this capital N times little o of 1 over n squared is what? This is little o of 1 over n, right? Okay. So I get that this composition Qn to Q1 is the same as Pn to P1 plus little o of 1 over n. Okay. Right. And
Yes.
this is what? This is parallel transport along the top curve, right? And what is this composition? Well, in this composition of the PIs, what happens is these vertical sides will cancel out, right? Because I'm going up once and then down again, and then up once and then down again. So these vertical sides will cancel out, right? So in the end, I'll just get parallel transport along this curve, right?
Yes.
Okay. So what I get is that parallel transport along this curve is the same as parallel transport along this curve plus an error which is little o of 1 over n. But the vertical sides are constant, right? The homotopy maps the vertical sides to constants, right? It's a fixed endpoint homotopy. So this parallel transport here is just identity. And this parallel transport along the vertical side is identity, right? Okay. Yeah. These paths are constant, right? These are just constant equal to the initial point P. And this is constant equal to the terminal point Q, right?
Yes.
So this composition is nothing but just parallel transport along the bottom curve, okay? So what do I get? I've got at the end that parallel transport along, so if I call my curves in the homotopy, say gamma 0 up to gamma n, right? These are the horizontal curves. All right. Yeah. So then this Qn to Q1, this is a parallel transport along gamma 1. And this Pn to P1, this is parallel transport along gamma 0. So what I get is parallel transport along gamma 1 is parallel transport along gamma 0 plus little o of 1 by n, right?
Yes.
And in fact, I get this for any I, that parallel transport along the I plus 1th curve, gamma I plus 1, by the same argument will be parallel transport along gamma I plus little o of 1 by n. Right? Okay. And so now I can add these up. And what do I get in the end? That parallel transport along the top curve, gamma n, is equal to parallel transport along the bottom curve, gamma 0, plus n times little o of 1 by n. Right? So therefore, that is equal to P gamma 0 plus little o of 1. Okay. Now you let n tend to infinity. So this converges to P gamma 0 as n tends to infinity. Is this clear?
Yes.
Okay. So therefore, parallel transport along the top curve is the same as parallel transport along the bottom curve. Is this okay?
Yes, sir.
Yes, Orkojit, is this all right? Yeah.
Yes, fine.
Okay. So it's similar to the proof of Cauchy's theorem, right? In complex analysis. I mean, except here we're using, instead of line integrals, we're looking at parallel transport, right?
Right. Yes.
Okay. And in Cauchy's theorem, what makes the integral over a small square 0 is basically that your function f is holomorphic. So the integral fz dz over a small square is 0, right? That you can sum up in one equation, d bar equal to 0, right? D bar f equal to 0. So instead of d bar f equal to 0, here we have the curvature tensor r equal to 0, right?
Right. Yes.
And that is leading to a similar conclusion at the end. Okay. So now we get that parallel transport only depends on your path up to homotopy, right? Okay. So now you take a ball in the manifold, right? So this is simply connected. So if I fix a base point P here, then for any Q up to fixed endpoint homotopy, there's a unique path joining them, right? Because the ball is simply connected. Yes?
Yes. Yes. Right.
Okay. So I can define unambiguously a parallel transport from P to Q, right? I just take any curve from P to Q. It doesn't, the choice of curve from P to Q, it doesn't matter because all curves from P to Q are fixed endpoint homotopic in this ball, right? Okay. So therefore, I can define for all so what I do is I fix EI an orthonormal basis of TPM, okay? And then I define vector fields, capital EI, vector fields on this ball B, okay? EI of Q is equal to the parallel transport along the, let's say the geodesic from P to Q. Say I take a geodesic ball, right? So I just parallel transport along the geodesic from P to Q of EI, all right? So this is a vector at Q, okay? All right. So
Yes.
this gives me orthonormal vector fields on the whole ball, right? Okay. Now the point is the covariant derivative of these orthonormal vector fields is 0 because if I take any, let's say any curve passing through Q, right? Suppose I take any gamma curve passing through Q with tangent vector V at Q, okay? Then the covariant derivative nabla V of EI, right? So the covariant derivative of EI at Q in the direction V. Well, what will this be? Well, this curve, I can always, join this curve to P by some curve, right? Yeah, I can extend this backwards to a curve passing through P, right? So
Yes.
then my EI is given by parallel transport along this curve gamma. So therefore, this is just, ddt with respect to the curve gamma of EI, right? And so this is 0 because EI is given by parallel transport along gamma. So therefore, my EIs are parallel everywhere, right? So these are parallel vector fields. Okay. Is this clear?
Yes, sir.
Okay. So then what? So this implies, so therefore, this implies that if I look at the bracket of EI and EJ, then by symmetry of the connection, this is nabla EI EJ minus nabla EJ EI. But both these terms are 0, right? Because my vector fields are parallel. Okay. So that means these
Yes.
vector fields commute, right? So now they commute. So therefore, when I have commuting vector fields, n pairwise commuting vector fields, then I can use them to define a coordinate system, right? Yes.
Yes.
Okay, so what you do is, if you let say phi I comma t, you let this be the flow of EI, right? Okay, then you get a map from a ball, say B0. So a ball around the origin in Rn. Okay, so to this ball around P. What do? You take a vector T1 to Tn and you map it to phi 1 comma T1 composed with phi n comma Tn of P, right? Yes? Okay. Now these flows commute because the vector fields, the brackets are 0. So actually this composition I can write in any order, right? Okay. Yeah. So let me call this map F. The claim is that this map F is an isometry, right? So why is that? Because if I look at the orthonormal basis of the tangent space in Rn at a point in this ball, that's given by the del del xi's, right? Or the del del ti's rather. My coordinates are ti's. So what do the del del ti's go? So what is df at a point T1 to Tn of this orthonormal basis vector del del ti? This by definition is del del ti of f, right? And what is this? So this is del del ti of this composition. But here what I can do is, since they commute, I can put ti in the first position, right? So this is del del ti of phi I comma ti, and then I put the rest, okay? Phi 1 T1, phi I minus 1 T minus 1, phi I plus 1 T I plus 1, phi n Tn. So I'm differentiating now just the flow of EI, right? Phi I comma T is the flow of EI. So when I differentiate the flow of EI, what will I get? I'll just get the vector field EI, right?
Yes.
Okay. So this will give me EI at the point f of the vector T. Is this clear?
Yes.
Okay, so therefore df at a point vector T maps the orthonormal basis del del xi to the orthonormal basis EI. So therefore df is an isometry. Okay. Is this clear?
Yes.
Okay, so that's it. So you get a local isometry. Okay, so locally the manifold is isometric to Rn. Is this clear? This is a sketch of a proof. Okay, you can make this more, you can put more details if you want and so on, but essentially this is the proof. All right. I mean, this is one proof. Yeah.
So we could have shown that exponential map is isometric, I think.
That is true. Yeah, that is true. That is true. The exponential map will be an isometry. Correct. Yeah, that's true. Yeah, that's true. That's true. That's true. But that doesn't follow from this proof. I mean, yeah. That will need a computation of the derivative of the exponential and so on.
Yes, yes.
Then you'd have to look at Jacobi fields and so on. And yeah.
Mhm.
So, yeah. So, yeah, you can do it like that using the exponential. That's true. You can do that. Yeah. That's true. This proof, this actually what it shows, the first part, that parallel transport only depends on the curve up to fixed endpoint homotopy. This is more general. You see, this argument works for any connection in a vector bundle over M, actually, right?
Yes, yes, right.
Okay, where you define analogously the curvature of the vector bundle and so on. So if the curvature of the vector bundle vanishes, then parallel transport is only depends on the fixed endpoint homotopy class. And what this gives rise to is what's called the holonomy representation of the fundamental group, right? Because so now if I have a loop, so this is general for what's called flat vector bundles over a manifold. So flat means it has a flat connection. That means a connection whose curvature is 0. So the curvature of a vector bundle is, it's a two-form with values in endomorphisms of the vector bundle, right? Just like the curvature of the Riemannian manifold was, there the vector bundle is the tangent bundle, right? And it's the curvature operator is a two-form with values in endomorphisms of Tn, right? So similarly, the curvature of a vector bundle given a connection will be a two-form with values in endomorphisms of E of your vector bundle, right? So the holonomy representation, this is a representation from the fundamental group of the manifold at the point P to, well, if you have a vector bundle, then basically what you're doing is, you see, here's your manifold and here's your vector bundle. Okay. And, well, okay, maybe I don't have a good picture here. Sorry. So if this is your manifold, and if I take a loop in the manifold like this, right, then basically I have parallel transport along this loop, right? And parallel transport along this loop will give me a isomorphism from the fiber to the fiber, right? So in general, for a vector bundle, this will go to GL of the fiber, where E is my vector bundle over M. Okay. So this works when the bundle is flat. Okay, for a flat vector bundle. Flat means the curvature is 0. Okay, so for us, in our case, E is just Tm, and nabla is the Levi-Civita connection. And the parallel transport is by isometries. And so, so actually this goes from pi 1 MP to the orthogonal group of TPM. Okay. Is this clear?
Yes.
Yes.
Right. I mean, this is well defined because parallel transport only depends on the loop up to fixed endpoint homotopy. And so elements of the fundamental group are exactly loops up to fixed endpoint homotopy, right? So this is well defined. Is this clear?
Yes.
Okay. And so the general picture, so we saw that M is locally isometric to Rn. The general picture will be if M is complete, you need a completeness hypothesis. If M is complete and flat, so flat means curvature is identically zero. Okay. Then M is so what happens is well, I think I'm stating this correctly. This holonomy representation will be a faithful representation, and so then M is isomorphic to TPM mod the image of rho. Okay, so this acts on the tangent space by isometries, and you look at the quotient, right? So this will give you a flat manifold. It's a quotient of Rn. Basically, it's a quotient of Rn mod a group of isometries. Okay, so gamma is a fixed point free group of isometries. So yeah. Let me think. I may not be stating this correctly. I'll have to look this up actually, to be fair. I'm not sure. But this is true that M is isomorphic to a quotient of Rn. Okay, so gamma is a discrete subgroup. Okay. Gamma is a discrete subgroup of isom Rn. Okay. And this gamma is isomorphic to pi 1m. Okay. Is this all right? Yeah.
Yes.
Okay. Okay. So these are flat manifolds. They're quotients of Rn in general, if they're not simply connected. If they're simply connected, then it will be isomorphic to Rn. Okay. Yeah. Okay, so let's stop here. We have less than a minute and we'll start a new session. Okay. Okay, so yeah, so I'm just sorry, I'm correcting what I said in the last session. So no, it's not true that M is isomorphic to the tangent space mod the image of the holonomy representation. That's not true. But it is true that M is isomorphic to a quotient of Rn. Okay, because and that you get because see, M is the quotient of M tilde, the universal cover by the fundamental group, and the fundamental group here acts by isometries. And if M tilde is simply connected, then this argument that we gave above to construct these vector fields EI, this or parallel orthonormal vector fields, we can make this argument global, right? If M is simply connected, then any 2 points, there is up to fixed endpoint homotopy, a unique path joining them, right? So then this argument becomes global, right? Yes, these parallel vector fields become global, right? Yes.
Yes, sir.
Okay. And so then we'll get that M is so if so M tilde will be flat also, and M tilde this will be isometric to Rn. Okay, by the above argument. And then the fundamental group will be conjugated to some group gamma of isometries of Rn, right? Okay. And so then M, which is M tilde mod pi 1 M, this will be isometric to Rn mod gamma. Okay. So that's the argument. Sorry. Yeah. Okay. Actually, the holonomy representation could be trivial. I mean, if I take a torus, right? So a torus, let's say a 3 torus. So that's a quotient of a flat cube by identifying the opposite sides. So here, the holonomy representation will be what? I mean, what will be a loop at this point? I go through this side, let's say, and then I come out this side, right? And I come back here. This will be a loop, right? So here parallel transport is just the identity, right? Yeah. Okay. The parallel transport will just be the identity in this case. So yeah, so the holonomy representation for a torus Rn mod Zn, the holonomy representation rho is trivial. Yeah, in this case, the representation is trivial. So if I go up also, then this way, here the parallel transport will also be trivial. Okay. Is that all right? Yeah.
We also have the holonomy group, right? So from this, we can consider its representation to say the holonomy group modulo is a connected component or something, that row, or
Sorry, what are you saying?
I'm saying that we can also consider the holonomy group itself. Okay.
The holonomy group is the image of the holonomy representation.
Oh, अच्छा, अच्छा.
Oh, okay. Yeah. Well, I mean, for a manifold which is not flat, then it's a larger group in the sense, I mean, you don't have a holonomy representation. If the manifold is not flat, then the parallel transport depends on the loop, not just the homotopy class.
Yeah.
Then you'll have to take parallel transport along all loops and look at all look at the group generated by parallel transport along all loops. Yeah, that's the holonomy group in that case. Yeah.
Yeah, and in that case, we need to see like relation between the fundamental group and the holonomic group.
Yeah, I mean, if the manifold is not flat, then I don't know anything about the relation really. I don't know. Yeah.
Okay, sir.
It's only if the manifold is flat you get a holonomy representation. And in general, for other representations, you need a flat vector bundle. So if you have a flat, so there's a one-to-one correspondence between, so this is called the Riemann-Hilbert correspondence between flat vector bundles and representations of the fundamental group. Okay. So
Can you write it down?
yeah, sure. Sure. So the Riemann-Hilbert correspondence so actually this came from studying first of all the hypergeometric equation which Riemann studied, and he studied the monodromy of the solutions of the hypergeometric equation. So the hypergeometric equation actually it's a second order differential equation. Yeah. So it corresponds to so anyway, let me write the Riemann-Hilbert correspondence. So on the one hand, you have flat vector bundles E over M And on the other hand, this is in one-to-one correspondence with representations rho from pi 1 MP to EP. Sorry, to GL of EP. Okay. So one direction you've seen, if I have a flat vector bundle, I get a holonomy representation. And the other direction is, if given a representation, you can construct a flat vector bundle. Okay. So for that, what you do is you take basically, so if I call V equal to EP, okay, so this is a vector space. So then what you do is you take the fundamental group M tilde cross the vector space V, okay, and then you quotient this by a diagonal action of the fundamental group. Okay, so the fundamental group acts on M tilde by deck transformations. It also acts on V via the holonomy representation, right?
Yes.
Yes, yes.
So you can quotient by the diagonal action. Okay, this is a diagonal action.
Right.
Then the quotient by the diagonal action will be a vector bundle over M. Okay, this is a vector bundle over M. And the holonomy representation of this vector bundle is exactly the given representation rho. Okay, so this is the other direction. Is this all right?
Yes, sir.
Sir,
Yes.
yes. I have a question that EIs, that vector fields you constructed, those are smooth only because you have that property, because the manifold is flat, right?
Well, look, see, you can define EIs on any geodesic ball to be smooth by taking just parallel transport along radial geodesics from the center of the ball.
But that might not be smooth, right? I mean, because radial directions, will it be smooth?
Yeah, this will be,
radially will be smooth, but tangentially, how do you say?
yeah, this will be smooth. This will be smooth. This will be smooth. Because I mean, the geodesics depend smoothly on the point, right? So I mean, the geodesics vary smoothly. So if I move in this direction, right, then they'll be smooth, but they won't be parallel. Their covariant derivative will not be zero. Their covariant derivative only along the radial direction will be zero. That's what happens. Right?
Okay, fine. Yes.
Does that make sense? Yeah.
Yes.
What by is that in the flat case, the covariant derivative in any direction is zero, not just the radial direction.
Yeah.
Right. So, yeah, in fact, these radial vector fields, these are useful to construct parallel vector fields. You can always construct parallel vector fields which are parallel at a point. So you can always construct the EIs, okay, on a neighborhood of P to be orthonormal everywhere, an orthonormal frame, okay. You can always construct an orthonormal frame, and this is useful such that at the point P, nabla V EI is 0 for all V in TPM. That's all, just at that point.
Yes. Right.
Is this all right? Yeah.
Yes.
Makes sense. Okay. So this you can do. Yeah. So this is useful. Yeah. This is useful. Yeah. Any more questions? So let me just state this. Always construct Yeah, so if you're interested in the Riemann-Hilbert correspondence, you should read about the classical story, which starts with the hypergeometric equation. Okay, so the hypergeometric equation is basically, you can think of it in geometric terms. The differential equation is given by, so it has three singularities. The hypergeometric equation, 0, 1, infinity. Okay, and so what you get is a rank 2 vector bundle, copies of complex vector bundle, C2. In fact, it's a holomorphic vector bundle. Okay, it's the trivial bundle, but with a connection. The connection is gives you the differential equation. So it's the trivial bundle with a holomorphic connection over the thrice punctured sphere. So then you take that connection is flat because it's a holomorphic connection over a Riemann surface, and what happens is its curvature 2 form is a 2-0 form, and in dimension 1, dz tensor dz is 0, so the curvature vanishes. So any holomorphic connection over a Riemann surface is flat, and so then you get a flat vector bundle. You take its monodromy, and that is the monodromy of the hypergeometric equation. Okay, so anyway, so yeah, for Riemann surfaces, this is a big story. So yeah.
So by monodromy, you mean what we learned in analytic continuation, that sort of thing?
Exactly, analytic continuation of the solutions. Exactly, analytic continuation of the solutions. Exactly. Yeah. Exactly. Yeah. Okay, so this is a nice classical story. There are books about it. I can send you some references if you're interested. So for the Riemann-Hilbert correspondence so this was actually a problem. I mean, you see, actually, look, I haven't done the full correspondence here. The thing is, given well, okay, fine, yeah. Well, what you wanted, see, I can always construct a vector bundle whose representation is rho, whose holonomy representation is rho by this abstract construction. But, in the 19th century, people wanted more concrete things, right? They didn't think so abstractly. They didn't have these abstract concepts. They wanted a concrete differential equation, which is called a Fuchsian equation, an equation with regular singularities. So you've studied regular singularities, right, of differential equations with meromorphic coefficients. So you wanted an equation with regular singularities whose monodromy representation was a given representation. Okay, and so this was an open problem for a long time, and so this was so yeah, I've forgotten the details of this, but I did teach a course on this once, so at Belur, so anyway, so I can go through that and let you know if you want to know more about it. So. Okay, sorry. So just digressing off, but anyway, I think it's interesting anyway to know these things. Okay, so now let's come back to the main subject matter. Okay, so for the rest of today, we'll talk about what are called Jacobi fields. Okay, so what are Jacobi fields? Okay, so these will be the main tool to study how curvature influences properties of the manifold. Okay, the main tool to study them will be Jacobi fields. So Jacobi fields are certain vector fields along geodesics which arise from considering variations of the geodesic through one parameter families of geodesics, say gamma S. Right, so if I have a one parameter family of curves in general, gamma S, then if I take the derivative with respect to the parameter S, then we get a vector field along gamma 0, right? The variation vector field. of this one parameter family of curves. So what happens is, if my variation of curves is through geodesics, then I get a very special kind of vector field along the geodesic. Okay. So those will be Jacobi fields. All right. So now, first of all, one parameter family of geodesics, you can think of that as, see, this will be a function of two variables, right? Gamma S of t. So this is a function of two variables. So I can think of this as a map from R2 into the manifold, right? Okay. So this leads us to what's called a parametrized surface. So that's a smooth map F from an open set in R2 into the manifold M. Okay. And just like we had vector fields along curves, we can talk about vector fields along a parametrized surface. So that will be a smooth map from the domain of the map F, U, into the tangent bundle. So a map V, such that V of ST lies at in the tangent space at F of ST. All right. So this is a vector field along the parametrized surface F. Okay. And given a vector field along a surface, so just like for a vector field along a curve, we had its covariant derivative dv dt. So for a vector field along a surface, we will have two covariant derivatives, dv del s and dv del t. Okay, these will also be vector fields along the surface F. So dv del s at a point s0 t0, how do you define this? Well, you fix the coordinate t0, you fix the second coordinate to be equal to t0, and then you look at s goes to v of s t0, right? So this is now a vector field along a curve. So I can take its covariant derivative, dds of this, all right? So that will be defined to be dv del s. Is this clear?
Yes.
And similarly, we can define dv del t, all right, by fixing the first coordinate equal to s0 and then taking the covariant derivative with respect to t. Okay, fine. So we have dv del s, dv del t, and we have always two natural vector fields, del f del s and del f del t, vector fields along F. How are these defined? So del f del s is simply, you fix again t0, t equal to t0, and then you take dds of this curve, s goes to f of s comma t0, right? So this will give you a tangent vector at f of s0 t0. So this will give you a vector field along F. And similarly, del f del t will be, you fix first coordinate equal to s0 and just take the derivative of f with respect to t. All right. So this will again be a tangent vector at the point f of s0 t0. Okay. So we have these two vector fields, del f del s and del f del t along F. Is this all right? Yeah.
Yes.
Okay. So now let's look at a special case. Suppose F is a diffeomorphism onto a two-dimensional submanifold of S, S of M. Okay. Right. So that means F is an embedding. Okay. So suppose F is an embedding. This is a special case. In general, F need not be an embedding. It might only be an immersion, or it may not even be an immersion. Okay. It could have critical points, whatnot. It could be just a general smooth map. But suppose we are in this nice case where it's a diffeomorphism onto a submanifold. Okay. So then, because S is a submanifold and F is a diffeomorphism, so vector fields along F will correspond to just vector fields on S, right? And vector fields on S, because S is a submanifold, locally I can extend vector fields on S to vector fields in a neighborhood in M, right? Yes?
Yes.
So then, and these vector fields, del f del s and del f del t, these I can write in the form x composed with f and y composed with f, where x, y are vector fields on a neighborhood of f of s0 t0, a neighborhood in M. Okay, I can extend my vector fields from S into a neighborhood in M, say V, and I call the resulting vector fields X and Y. So then del F del S and del F del T are given by restricting the vector fields X and Y to the surface, the image of F. All right. Okay.
Yes.
So then what does this mean? This means that, in fact, the coordinate vector fields del del S and del del T on R2, these will be F related to the vector fields X and Y, right? Yeah. What is del F del S? This is df of del del S, right? And del F del T is df of del del T, right? So df maps del del S to X and df maps del del T to Y, right? So that means they're F related. Yes?
Yes.
Okay. So now we know that, so del del S, del del T, these are the coordinate vector fields on R2. So their bracket is 0, right? And we know that for F related pairs of vector fields, the brackets are also F related. So that means that this bracket del del S, del del T is F related to the bracket of XY, right? And so that means 0 is F related to the bracket of XY. That means what? That means that XY is 0 on S, right? The bracket of XY is 0 on a neighborhood of this point F of S naught T naught in S. Is that clear?
Yes.
Okay. All right. Now let's look at capital D del T of this vector field del F del S along F. Okay. So by definition, this is what? This is capital D dt, the covariant derivative of the curve T goes to, of the vector field along a curve, T goes to del F del S of S naught comma T, right? Okay. Now del F del S of S naught comma T, this I can write as X of F of S naught T. Okay. So this is just the covariant derivative of X along a curve. So this is going to be nabla sub the tangent vector to this curve, right? At of X. So this will be, and the tangent vector to this curve, F of S naught T. So d dt at T equal to 0 of F of S naught at T equal to T naught, this should be. This is equal to Y at the point F of S naught T naught. So this will be just nabla sub Y of X, right? At F of S naught T naught. Is this clear?
Yes.
Okay. Similarly, d del S of del F del T, this will be nabla sub X of Y at the point F of S naught T naught, right? Okay. Now, the bracket of XY at the point F of S naught T naught, this is 0 as we've seen above. Therefore, by symmetry of the connection nabla, what do we get? We get that d del T of del F del S, this is equal to nabla YX, but because bracket XY is 0 at this point, so at this point, this is also equal to nabla XY, right? Yes, by symmetry.
Yes.
Yes, sir.
Okay. This is equal to d del S of del F del T. So therefore, what do we get? We get this relation for this parametrized surface, d del T of del F del S. This is equal to d del S of del F del T. Okay. So this follows from symmetry of the connection. Okay. Is this all right?
Yes.
Yes, yes.
Okay. Now we can also derive another relation. So if I take a vector field V along F, then locally again I can write V as a restriction of some vector field Z to the surface, right? Yeah. Okay. So Z is again a vector field in a neighborhood in M of the point F of S naught T naught. And so similarly, as we did above, dv del s, this is going to be what? This will be nabla x of z composed with f, right? And dv del t will be nabla yz composed with f. Is that clear?
Yes.
Right? So now if I look at d del t of d del s of v minus d del s of d del t of v, what will this be? So d del t corresponds to nabla y, right? So this will be nabla y, nabla xz minus nabla x, nabla yz, the whole thing composed with f, right? Okay. Is this clear?
Yes, sir.
And so what is this? Since the bracket of xy is 0 on S, right? So this is just equal to the curvature tensor, right? The curvature operator acting on x, y, z, right?
Yes.
Okay, so this is equal to R of x, y, z composed with f. And x and y correspond to del f del s, del f del t. So finally we get this relation that for any vector field v along f, d del t, d del sv minus d del s, d del tv, this is equal to R of del f del s, del f del t v for all vector fields v along f. Okay. So basically, when you take the commutator of the two covariant the covariant partial derivatives with respect to t and s, you get a curvature term. Is this clear?
Yes, sir.
Okay. Now, this we proved assuming that f was an embedding, right? Onto a two-dimensional submanifold, a surface embedded in M, right? Okay. So we proved these two relations, that d del t del f del s is d del s of del f del t, and we proved this commutation relation. Okay. But it turns out that these two relations actually hold for any parametrized surface. Okay. So I won't prove that. I just did this to give you motivation for the following statements. So for any parametrized surface, we have d del s of del f del t is d del t of del f del s, and d del t dv del s minus d del s dv del t is R of del f del s del f del t v for all vector fields v along f. Is this okay? Okay.
So the curvature signifies how far the covariant derivatives of the respective vector fields commute or not.
Correct. Correct. I mean, that you've seen in the, look, this in the definition of curvature tensor, you see that, right? It's just measuring the difference between nabla y, nabla x, and nabla x, nabla y, right? So the point is, I mean, you have this for the vector fields along the surface F also, right?
Yes.
Okay, this can be expressed in terms of the curvature tensor. Okay. So we proved this when F is an embedding, and in the general case, this is also true. That's all I'm saying. Okay.
Yes, sir.
Okay. So now we're going to use these two relations to study these Jacobi fields. Okay. So now, suppose I have a one-parameter family of geodesics. So I have a parametrized surface of a very special kind. So let's say it's a map from an interval minus epsilon epsilon cross an interval I into M. Okay. So this is a parametrized surface given by a one-parameter family of geodesics. So that means for every S in the interval minus epsilon to epsilon, the curve gamma S of t, this is defined to be f of st. This is a geodesic. Okay. So if I fix S, then as a function of t, I get a geodesic in M. Okay. So I have a smooth one parameter family of geodesics. All right. So then what can I say about this parametrized surface? Well, if I look at d del t of del f del t, this is going to be 0 because this is what? This is just, so del f del t is going to be the tangent vector to this geodesic gamma s prime, right? Okay. And gamma s is a geodesic. So its covariant derivative with respect to t will be 0. So therefore, d del t of del f del t will be identically 0, right?
Yes.
Okay. That's just because each of the curves gamma s is a geodesic. All right. So now this is where we're using the fact that we have a one parameter family of geodesics. Okay. Therefore, we can now differentiate this equality. So this is a vector field along F. I can take its covariant partial derivative with respect to S, right? So d del S of this thing will also be 0, okay? Yes?
Yes.
Yes, sir.
But now what do I have? I have a composition of two covariant partial derivatives, d del S and d del T. So by this relation 2 above, I can replace this d del S, d del T. I can take this to the other side, and this will be equal to d del T, d del S minus a curvature term, right?
Yes.
Okay.
Yes.
So I do that here. So this becomes d del T, d del S of del F del T minus R of del F del S, del F del T applied to del F del T. Okay. Is this all right?
Yeah.
Okay, I'm just using the equation, this equation above here. Okay. To interchange these two covariant derivatives. Okay. Now, look at this term inside here. This is d del S of del F del T, right? So by the first property here, this property basically follows from symmetry of the connection. I can replace this by d del T of del F del S, right? So this then becomes, this first term becomes d del T of del F del S, right? Okay, using property 1. And this term here, the curvature operator is alternating in its two arguments. So minus of this, I can interchange these two, right? And I can write this as plus R of del F del T, del F del S. I just interchange these two and change the sign, right?
Yes.
Okay. So finally, I get this, okay? And now, if I evaluate this at S equal to 0, so when S is equal to 0, I get a geodesic gamma, which is gamma naught of T, which is F of 0T, okay? Then my del F del S, this is going to be at S equal to 0. This will be a vector field J along gamma. So J of T is going to be del F del S at 0 comma T, okay, when S is 0. So this is going to be my Jacobi field. This is the variation vector field of this one parameter family of geodesics, right? I'm differentiating with respect to the parameter. Yes, S at time S equal to 0. Okay. So I substitute del F del S. This will become J, right? So then what do I get? I get J here, and then I get the second covariant derivative of J plus R of, so del F del T will be gamma prime, right? This will be the tangent vector to the geodesic gamma. Okay, this becomes gamma prime. Del F del S will become J, and del F del T again will become gamma prime, right? So therefore, what we get is that the vector field J satisfies the following second order ODE along the curve. Second covariant derivative of J d squared j dt squared plus r of gamma prime j comma gamma prime is equal to 0. Is this clear?
Yes.
Yes, sir.
Okay. So this equation is called the Jacobi equation. Okay. And so now we can define a Jacobi field to be a vector field J along a geodesic gamma, which satisfies this Jacobi equation. Okay. All right. So that's the definition of a Jacobi field. It's a vector field along a curve, a geodesic, sorry, which satisfies this second order linear ODE. All right. Okay, so any variation vector field of a one parameter family of geodesics, as we've seen, gives us a Jacobi field. Okay. So let me stop this meeting now and start a new one. Okay.
1 minute. Thanos.
Yeah, we can take a couple of minutes break. Sure. All right. Okay, so we've seen that when you take a one parameter family of geodesics, if you differentiate with respect to the parameter S, then you get a vector field J along the initial geodesic gamma, which satisfies this Jacobi equation, which is a second order linear ODE in the vector field J. Okay. And then we take this ODE as our starting point now, and we define a Jacobi field to be a vector field J along a geodesic gamma, which satisfies this Jacobi equation. Okay. So the first thing is to see that since this is a second order ODE, right, this should be determined by a pair of initial conditions, J0 and J prime 0, right?
Yes.
So let's see that. So let's first write this with respect to a parallel orthonormal frame along the geodesic gamma. Okay. So let EI be a basis of the tangent space at some point gamma T naught along the curve, and then extend these this basis to a basis of parallel vector fields, capital EI along gamma. Okay. Then if I take any vector field J along gamma, I can write J as summation AI EI, right? And now let me write R of gamma prime EI gamma prime. So this is going to be again a vector field along gamma. So again, I can write this as a linear combination of EJs. So summation over J, Bij, EJ, right? Okay. So then J will be a Jacobi field if and only if it satisfies this equation. So now what will the second covariant derivative of J be? Well, because the EIs are parallel, J double prime will just be summation AI double prime EI, right? Okay. Right? So that is the first term. And then this R of gamma prime, J gamma prime, I substitute J equal to summation EI over here. And I just use linearity of multilinearity of R. So this will become a sum over I, AI, R of gamma prime, EI gamma prime, right? Okay. So now R of gamma prime, EI gamma prime, this I substitute equal to sum over J, Bij, EJ. Okay. So I get this equation now. J is a Jacobi field if and only if sum over I, AI double prime, EI plus sum over I AI into sum over j Bij Ej. The whole thing is equal to 0, right? And now I want to write everything as a linear combination of the vector fields Ej. So here I just reverse the order of summation. And so then I get the following: the sum over j of Aj double prime plus sum over I Bij Ei, the whole thing into Ej. This sum is 0, right? Yes, is that okay?
Yes, sir.
And since the Ej's are a basis, this means that each of the coefficients by a system of second order linear ODEs, Aj double prime plus sum over I Bij Ai equal to 0, right?
Yes.
So the of the conditions VW, which are both tangent vectors at gamma t naught, there exists a unique okay, right? Because this is yes. Okay, like so AI prime 0. So uh, so therefore 0, right? Yes,
Yes.
Yes, sir.
right? Yes.
Yes, sir.
So therefore, sorry, what are you saying, Utshap? Sorry,
Yes, sir.
what did you say, Utshap?
Yes, sir. It's fine.
Yes,
Oh,
sir.
right. So therefore, given J, uh, yes, it's fine, right? Okay. So okay. So these are vector fields J along gamma subset. So this J gamma is a vector space goes as the Jacobi field along gamma. So uh, on to, therefore, the isomorphic to the tangent space directs some. Is this okay? Okay. Okay, so right. So suppose we take J1 to be the vector field gamma prime along gamma. So let's look at the Jacobi equation for J1. So J1 double prime plus R of gamma prime J1 gamma prime. This will be d dt of gamma prime plus R of gamma prime gamma prime gamma prime. And since gamma prime is a geodesic, the first covariant derivative already ddt of gamma prime is 0. And this term is 0 because R is alternating. So R of gamma prime is 0, right? Okay. So this will be 0. And so therefore, this J1 is always a Jacobi field. This tangent vector field, this is always a Jacobi field. Okay. And what is it? What are its initial conditions? So J1 of 0 is just gamma prime 0. And J1 prime 0 is 0 because gamma double prime is 0, right? It's a geodesic. So the initial conditions are gamma prime 0, comma 0. Okay. Now we can get another. So this Jacobi field is tangent to the curve, right? So it's called a tangential Jacobi field. It's tangent to the curve. We can get a second tangential Jacobi field, J2. This is T times gamma prime T. So now if we look at the Jacobi equation for this, first we have to calculate J2 prime. So by the Leibniz rule, this is going to be 1 into gamma prime plus T into ddt of gamma prime. So ddt of gamma prime is 0. This term vanishes. So you just get 1 into gamma prime. So J2 prime is gamma prime. Okay. So therefore, J2 double prime is ddt of gamma prime. This is 0, right? So if I look at the Jacobi equation, then the first term J2 double prime vanishes. And the second term R of gamma prime, J2 prime, gamma prime. This is R of gamma prime, T gamma prime, gamma prime. So the T comes out and this again becomes R of gamma prime, gamma prime, gamma prime, which is 0. So this term also vanishes. So therefore, J2 is also a Jacobi field. All right. Yes. Okay.
Yes.
And what are the initial conditions for J2? So J2 0 will be 0. When I put T equal to 0, I get 0. And J2 prime 0, well, J2 prime is gamma prime. So J2 prime 0 will be gamma prime 0. So this has initial conditions 0, comma gamma prime 0. Okay. Is this all right?
Yes, sir.
Okay. So now let P be gamma 0 and let V be the vector gamma prime 0 in TPM. And let W be the two-dimensional subspace of TPM, direct sum TPM, given by the span of the two vectors V comma 0 and 0 comma V. All right. So then since J1 and J2, these have initial conditions exactly these two vectors, V0 and 0V. That means that under the isomorphism that we described above, sending a Jacobi field to its initial conditions, j prime 0, j0 comma j prime 0. Under this isomorphism, the span of j1 and j2 maps to this subspace W, right? Yeah.
Yes. Yes.
Okay, so in particular, I mean, these J1, J2 are linearly independent, right? Because they map to linearly independent vectors V0 and 0V. Okay, so these Jacobi fields are linearly independent, and their span maps to this subspace W of TPM, direct sum TPM. Okay. So now we can define what is called the space of normal Jacobi fields. So this will be a subspace of the space of Jacobi fields. So this is J sub n of gamma, the normal Jacobi fields along gamma. So this is defined to be Jacobi fields J along gamma, such that the inner product of J with gamma prime is identically 0 for all T, right? So the Jacobi field is perpendicular to the curve at all points, all right? And okay, so what do we have so far? We have these two tangential Jacobi fields, gamma prime and T gamma prime. And what we want to do is actually say that this gives us a two-dimensional subspace of the space of Jacobi fields. And we want to say that the whole space of Jacobi fields is actually the direct sum of this tangential Jacobi fields. So these are trivial solutions to the Jacobi equation. These are always solutions. So the direct sum of these two trivial solutions together with the space of normal Jacobi fields. Okay, so we want to give a decomposition of any Jacobi field as a sum of a tangential and a normal Jacobi field. Okay. So let's see how we can do that. So first, notice if I have a Jacobi field J, then if I look at the inner product of J with gamma prime as a function of T, time along the geodesic, then what is its second derivative? So d squared dt squared of this inner product J gamma prime, this is ddt of the first derivative of this. If I differentiate this once, what do I get? I'll get inner product of J prime with gamma prime plus inner product of J with gamma double prime, but gamma double prime is 0. So this is just inner product of J prime with gamma prime. So if I differentiate this again, then I'll get inner product of J double prime with gamma prime, right? Okay. And now, because J is a Jacobi field, J double prime, I can replace by minus R of gamma prime, J gamma prime, right? So when I take the inner product with gamma prime, this is going to give me 0, right? Because this linear map, R of gamma prime comma J, this, as we saw last time, this is a skew symmetric linear map, right? So acting on gamma prime, the inner product with gamma prime will be 0. Is this okay?
Yes, sir.
So therefore, we get that this function of T, its second derivative is 0. So therefore, this inner product J gamma prime, it must be of the form some constant A plus a constant B into T, right? Because its second derivative is 0. So it's just a polynomial of degree 1, right? So how do I get the constants A? So A is the value at time 0. So when I put T equal to 0, then I get A equal to inner product J0 with gamma prime 0. And B is the derivative. So at time 0. So if I differentiate at time 0, then the derivative will be inner product J prime 0, gamma prime 0. So B is inner product J prime 0, gamma prime 0. Okay. So therefore, I get that inner product JT gamma prime T is inner product J0 gamma prime 0 plus inner product J prime 0 gamma prime 0 into T for any Jacobi field. Okay. Is this all right?
Yes, sir.
So now suppose I have a Jacobi field J, then it is a normal Jacobi field. So if and only if this function inner product J gamma prime is identically 0, but that is true if and only if both of these coefficients are 0, right? This inner product J0 with gamma prime 0 has to be 0, and inner product J prime 0 with gamma prime 0 has to be 0. So this is true if and only if inner product J0 with V is 0 and inner product J0, J prime 0 with V is also 0. So what does that mean? That means that the pair J0 comma J prime 0, this is perpendicular to both the vectors V0 and 0V in the direct sum, right, of TPM with TPM. In other words, J is a normal Jacobi field if and only if its initial conditions J0, J prime 0, these are orthogonal to W. Okay. So that means under the isomorphism phi, the space of normal Jacobi fields maps exactly to W perp. Is this clear?
Yes.
Yes.
Okay. So therefore, the space of normal Jacobi fields has dimension 2n minus 2. And since W direct sum W perp is TPM direct sum TPM, and phi is an isomorphism, we get that the space of Jacobi fields J gamma will be equal to the space of tangential Jacobi fields, which is the span of J1 and J2, the two trivial solutions to the Jacobi equation, direct sum the space of normal Jacobi fields. Is this clear?
Yes, sir.
Okay. All right. So, I mean, this normal Jacobi fields, this contains all the non-trivial solutions of the Jacobi equation. Is it clear? This J1, J2 are trivial solutions. These are always solutions for any geodesic gamma. You have these two solutions always, which are tangent to the curve. The normal Jacobi fields are the non-trivial solutions. Okay.
Yes.
All right. Now, as we saw earlier at the beginning, if F is a one-parameter family of geodesics, a parametrized surface which gives a one-parameter family of geodesics, then J equal to del F del S at S equal to 0. This is a Jacobi field along gamma, okay, which is F of 0 comma T. All right. Now, we can reverse the this correspondence. So, right, okay. Let me see. So let gamma be a geodesic and P is as before gamma 0 and V is gamma prime 0. Okay. So suppose V is in the domain of XP. So that means the geodesic gamma with initial condition gamma prime 0 equal to V. Suppose this is defined for time 1 at least. Okay. And now let W be a tangent vector to V in TPM. Okay. So the tangent space to V at tangent space of TPM at V, since TPM is a vector space, this is naturally identified with TPM itself. Okay. So I can think of W as an element of TPM. Okay. So now let V of S be a curve in TPM such that V0 is V and V prime 0 is W. Okay. So this is a curve in the tangent space TPM, which passes through V at time 0, and so that V prime 0 is W. Okay, so let me just draw you a picture so that you can see. So, so in the tangent space, I have a vector v, which is v0, and then I'm taking a curve in the tangent space. Okay, so this is my TPM. And the tangent vector to this curve is v prime 0, okay, is some w, which is also a vector in TPM. Okay, and then what I can do is I can look at the exponential of this. Okay. So each of these vectors, if I take the vector v of s, right, that's going to give me, if I look at the straight line through this, the straight lines through these vectors, those are going to give me geodesics passing through P, right? Okay, so this will be my initial geodesic gamma. And this point, say, is xp of v. This is gamma of 1. Okay, and here I get another geodesic. This will be the geodesic with initial condition v of s. So this is xp of tvs, right? Okay, so this gives me a one parameter family of geodesics. F of st is equal to xp of tvs, right? Yes?
Yes.
So this one parameter family of geodesics will give me a Jacobi field, right? Okay. So to get that Jacobi field, what do? I have to differentiate with respect to S, right? So this will be JT will be DDS or del del S at S equal to 0 of F of ST. Okay. So this will be del del S at S equal to 0 of XP of TVS, right? Okay. So if I do this at time 1, okay, then J of 1 will be what? J of 1 will be del del S at S equal to 0 of XP of VS, right? Now, VS is a curve in the tangent space whose derivative at time 0 is W. So by the chain rule, this will be the differential of the exponential map at the point V applied to W, right? By the chain rule. Yes? Right, since V0 is V and V prime 0 is W. Is this clear?
Yes, sir.
Okay. So we see that the derivative of the exponential map can be expressed in terms of a Jacobi field, right? The value of a Jacobi field at time 1. Now, all we need to work out is what are the initial conditions of this Jacobi field, right? That will determine the Jacobi field uniquely, right? So let's see what is J0. So J0 is going to be 0, right? Because if I put t equal to 0, then xp of 0 is always p. So this will be the derivative of a constant, right? This is f of s comma 0. F of s comma 0 is just constant equal to p, right? So this is 0, okay? So J0 is 0. Now let's work out J prime 0, right? So how do we get J prime 0? So J prime 0 is going to be d del t at t equal to 0 of del del s at s equal to 0 of f of st, right? Yes?
Yes.
But now we can use the symmetry property for parametrized surfaces. This is the same as d del s, right? At s equal to 0 of del del t at t equal to 0 of f of st, right? Okay. But f of st, this is a geodesic. So its derivative with respect to the time parameter this is just going to be gamma s prime 0, right? Where my geodesic so f of st is x p of t vs, right? So this is a geodesic with initial condition vs, right? So if I call this, say, gamma s of t, right? Then what is gamma s prime 0? Gamma s prime 0 is just vs, right? Yes?
Yes.
So this is going to be then d del s at s equal to 0 of vs, right? But now the vs's all lie in the same tangent space, TPM. So the covariant derivative is just the usual derivative, right? If you're in the same tangent space, okay? And so this is nothing but v prime 0, which is equal to w, okay? So finally we get that the following. So for all v in TPM, well, in the domain of the exponential, yeah, for all w in the tangent space 2 TPM at v, which we identify with TPM itself, okay, the derivative of the exponential at v applied to w is equal to j1, where j is the unique Jacobi field with initial conditions j0, j prime 0 equal to 0 comma w. Okay, is this clear?
Yes, sir.
Okay. So therefore, we have a formula for the derivative of the exponential map in terms of Jacobi fields. Okay. So this is why one of the main reasons why Jacobi fields are useful is because they allow you to express the derivative of the exponential map. Okay. Is this all right? Yeah.
Yes, sir.
Okay, fine. So yeah, we're almost out of time. So let me stop here. If you have any questions, you can ask. Yeah. So this is what we've proved. The derivative of the exponential at V acting on W is J1, where J is the unique Jacobi field such that J0, J prime 0 is 0, W. Okay. So any questions? Okay, so I mean, basically you're looking at geodesics close to this geodesic gamma, and this tangent vector here, this is J of 1, which is the image of the tangent vector here under the derivative of the exponential. Okay. All right then. So if there are no questions, let me stop here. And so next week we'll meet again on Wednesday. Okay, 2 to 4 Wednesday.
Okay.
Okay. So see you then on Wednesday. Okay.